In this video, we're going to look at how the Kotlin native compiler takes Kotlin IR and converts it to LLVM IR. How does the backend of the compiler work? So let's look at a very simple example. Here I have a main method which calls a method called add, which takes in 2 arguments and returns a result, which is the sum. And I could use the Kotlin native command line command to be able to generate a binary for this, and it will generate a KXC file which I could execute on a Mac. So if I could also print out the bit code for it, and this is what it will look like. In this video, we're going to look at the internal pipeline that generates this bit code, and I'm specifically going to focus on the backend piece of it. So the Kotlin native pipeline has a couple of stages. The first stage is to be able to hook into the front end of the compiler to be able to do parsing and analysis. Then it uses the K2 analysis APIs to be able to generate IR. So that IR is lowered and there are optimizations, transformations performed on it. And then it takes the Kotlin IR and is able to convert it to LLVM IR and does optimizations on that. And ultimately you get code generation linking, you get what you saw, which was the binary and the bit code. So specifically going to focus on the backend piece of it. So let's start with the architecture. The first thing that happens is that you give to the Kotlin native compiler configuration, whether it's through Gradle or whether it's through the CLI tool. So that's fed into the heart of the Kotlin native compiler, which is the entry point of it, which is the compiler driver. And the compiler driver works with a phase engine. And the phase engine allows you to construct either a binary or a C library or an Objective-C framework, or it could produce a klib. So one of these different processes depends on what you're looking for. So when I use the -o command in my command line, it was able to give me a binary, but I could also ask it to give me either a C library, and for Objective-C artifacts, it uses the Objective-C framework path. So the phase engine is an important concept in the Kotlin native compiler. There are a lot of different phases which are responsible for different things, and the phase engine gives you an API to be able to execute a phase. So a phase engine is comprised of an API which has a method called run phase, takes in a phase and it produces some result. And it has methods to execute logic for the front-end logic, for converting PSI to IR, and then also for running the back-end piece of the Kotlin native compiler. So the phase engine is divided into these different pieces, and these different pieces are executed when you're producing either a binary or a C library or Objective-C artifact. So the run phase, the front end of it, has front end phases that are run. And then also there are phases for converting PSI to IR and also for back end phases. There are also phases to do optimizations. So what is a compiler phase? And a compiler phase is comprised of first the name of it. The name allows you to do debugging. You could get reports, which I'll show you, performance reports on which phase took how long. You could also give it some prerequisites. So sometimes some phases have no prerequisites, some of them do. And then you could also give it some conditions that need to be satisfied. You could also give it some actions to run before the phase is executed and after it's executed. And the main heart of a compiler phase is the body, the main piece of the logic that it needs to execute, whether it's converting from IR to LLVM IR, whether it's performing some optimization. So the phase body takes in some input, whether it's a source file, and it gives you some result, some output. So let's look at first a front end phase and what that does and how it looks like. The front end phase hooks into the front end of the compiler. So it takes your K2 file, which is your source, and it feeds it to the front end of the compiler, does some analysis on that, and it gives you back a result. And when it's doing analysis, what it's using is the APIs that are provided in the front end of the compiler, in the front end module. If you look closely into that analyzer module right there, that's what it taps into to be able to do initial analysis on your source code. So the next thing that it does is that it converts the PSI. The next step to do after doing analysis is converting the PSI to IR. But what I'm going to focus on more is the backend piece of it, where it takes that IR and then it has to work with LLVM. So the backend of it takes basically the IR and it has to convert it to LLVM IR, and then it has to generate some binary file, some bit code. And in order to do this, what it does is that it uses this method. So this is an API, an extension on the phase engine, and it has 3 different stages. The first one is to run the backend code gen. And the next step that it does is that it executes some optimizations. You could see right there's a method called run bitcode post-processing, where it does some further lowering. And the last step there is to be able to create that bitcode file. So what it does, in order to be able to take Kotlin IR to generate an LLVM IR, there are Kotlin bindings that it's using. When you look closely in the LLVM interop module, you'll see this file right there, which has all the Kotlin bindings, and they look like this. So LLVM provides you with an API and that you could use, and there are Kotlin bindings that the native compiler has in this module that it utilizes to be able to do code generation, to be able to convert the IR to LLVM IR. So there is a visitor inside of the compilers that specifically does this. It goes through each piece of your IR module fragment and then converts different pieces of it, creates declarations, creates function calls for it. So this code generator is really important, which does this. This visitor goes in your code, and it has visit methods like visit function, visit declaration. So this is what the IR looks like right there. That's the Kotlin IR. So in order to be able to get that IR, and if you're doing debugging, you could use a specific compiler flag for that called xprint IR, and it will give you what the IR module fragment looks like. So it's basically that code generator is taking this and going through each piece of it to be able to generate the LLVM IR. So there is a visit simple function method, for example, which takes in a declaration IR simple function. And it's basically calling this method called generate function, which has all the logic. And what it uses internally is this wrapper. This is LLVM callable wrapper around. You can see right there, there's a type called LLVM type ref, which comes from LLVM, the Kotlin binding. And this is a wrapper around it to be able to create this callable. And it does this for this piece of code. And at the end, what this will look like when it takes this Kotlin IR, it will basically generate this piece right there. That's right. That is the generated LLVM IR. And in the Kotlin native compiler, you could look at it before and after. There are compiler flags that you could set to be able to get an output of this. So when it goes through this is what the resulting LLVM IR looks like right there. And now this last phase is to be able to take this and do some optimizations, convert it to a bitcode file. So that's what this piece does. It does some post-processing on that. And the last phase is to be able to take that and generate a bitcode file. So you could look at the bitcode for it by using this compiler flag print bitcode, and this is what it will look like, the final piece of it. So another thing that you could look at is the performance. You could look at how long did each piece take, which is by using this flag called dump pref. And it has you could supply a file that you want to create. And you could see right there that in a file called simple pref, you could see all the different stages, all the different phases, like how much did the analyze take, generate take, the IR lowering and IR generation, translation, how long did that all take? So you could get a really good performance on it. You could also get detailed analysis on how long each phase took. In the phase engine, when it was executing all the different phases, how long did they take? You could also get an output for that, a performance analysis on that. So this is a really brief snapshot of the internal pipeline and internal architecture. In the next videos, I'll go more in detail and look at one of the phases. I hope that was helpful.